Hi and welcome to our presentation on the material analysis of the University of New South Wales Anzac Braid Light Rail Station. This light rail stop is a crucial part of Sydney's L3 line and supports thousands of students and their staff commuting to and from UNSW Kingston campus. Our objective is to report, in this report, was to identify key structural and non-structural materials used in the station, evaluate their performance, and assess their sustainability using a life cycle sustainability assessment, also known as a LCSA. Based on this analysis, we will provide suggestions for viable material changes that could help to further align this station and others like it with environmental, economic, and social sustainability goals.
Let's begin with the primary structural materials. The station's core structural component is reinforced concrete, used for the platform and track slabs. Its high compressive strength makes it ideal for supporting the static and dynamic loads from passengers and trains. Concrete also offers weather resistance, fire durability, and long-term strength, which are all crucial for public transport infrastructure. While concrete has high compressive strength, its tensile strength is low, which is why it's reinforced with steel bars. These rebar elements handle tensile and shear forces and provide ductility. This allows engineers to design for safe and predictable failure. Alongside concrete, structural steel is also used in the station's framing. Its high tensile strength, corrosion resistance, and flexibility allow it to withstand Sydney's coastal conditions. Off-site prefabrication of steel elements also reduces construction time and site disruption, which improves efficiency and safety. These materials form the backbone of the station and were selected for their proven reliability in public domain projects. Now let's look at the non-structural materials. Non-structural materials at the station were chosen to support functions, safety, and aesthetics. One major element is bronze cladding, used for the canopy. Bronze is corrosion resistant and low maintenance, making it ideal for Sydney's coastal conditions. It also develops a visually appealing patina over time, contributing to the station's aesthetics and community appeal. Aluminum composite panels, or ACPs, are another key material. These are used primarily for station side signage. ACPs are lightweight, durable, UV resistant, and easy to fabricate. Their modularity aligns well with the station's clean and simple signage design standards. Lastly, concrete pavers were used for the pedestrian platform. These offer durability, slip resistance, and a modern appearance. Their modularity makes maintenance easy since individual pavers can be replaced without disturbing the surrounding materials.
From an environmental standpoint, concrete production has a high footprint. Producing a cubic meter of concrete emits about 43 kilograms of carbon dioxide and requires 570 megajoules of energy, mostly from limestone extraction and cement manufacturing. Water use is also high, averaging 160 liters per cubic meter of cement, not including mixing or on-site curing. Despite these environmental impacts, concrete is recyclable. At its end of life, the material can be crushed to recover steel rebar and aggregates. These can then be reused in road-based layers, drainage systems, or non-structural fills, though structural reuse is limited due to reduced strength in the recycled aggregates. Economically, reinforced concrete is relatively inexpensive, costing $200 to $300 per cubic meter in Sydney. Its lifespan of 50 to 100 years also makes it cost-effective for long-term infrastructure. From a social perspective, concrete supports public safety. The ductility due to steel reinforcement allows engineers to predict failure under stress, and installation risks are low when safety standards are followed. To enhance sustainability, we suggest using supplementary cementitious materials, or SCMs, like fly ash in the concrete mix. A 45% SCM mix can cut emissions by 35 to 40%, reduce water use, and lower dust production. SCMs are often more cost-effective than cement as well, and can result in improved worker safety and community health due to reduced dust and pollutant output. For reinforced concrete, we also explored cross-laminated timber, or CLT, as a sustainable alternative. CLT is manufactured by gluing together layers of timber at a 90-degree angle, which allows it to carry large loads comparable to that of concrete. This alternative is renewable, has high load capacity, and sequesters carbon. It's not suitable for tram tracks, but it could replace concrete in non-critical load areas like the stairwells or platform edges.
Concrete pavers, like reinforced concrete, use cement and aggregates. As a result, they carry a similar environmental footprint, especially in production and transport. However, they make up for this with better life cycle performance. Their modular design allows individual replacements, which is more sustainable and cost-effective than demolishing and repouring a full slab. When sourced locally, pavers can help to reduce transportation emissions, and they improve urban sustainability by reducing water runoff and enhancing groundwater recharge. This helps mitigate the urban heat island effect and supports water-sensitive urban design. Economically, although pavers might have a higher upfront cost, their low maintenance and long service life, up to 100 years, make them more cost-effective in the long run. Socially, they promote pedestrian safety. Their slip-resistant texture reduces the risk of falls in wet conditions, and their permeability reduces puddling and water-related hazards. To enhance sustainability, we first suggest exploring alternative material options. For example, a strong replacement is EnduroPlank, a recycled plastic decking material developed by Replis. Made from 85% recycled plastic, it is UV, rot, and moisture resistant, and aligns with circular economy principles. It's also low maintenance, cost-effective over time, and aesthetically adaptable. However, because transition from concrete reliance in the construction industry can be hard, using supplementary cementitious materials, SCMs, like fly ash in concrete pavers is a viable solution that still enhances sustainability.
Alright, to close, I'll summarize our key findings and recommendations. Our analysis found that both reinforced concrete and concrete pavers offer excellent economic and social sustainability, especially in the context of public infrastructure. They're reliable, cost-efficient, and ensure public safety. However, they fall short environmentally due to the high energy consumption, CO2 emissions, and water use. Despite this, their sustainability can be enhanced in meaningful ways. For reinforced concrete, using SCMs like fly ash and incorporating CLT in low-load applications can reduce its footprint. For concrete pavers, transitioning to recycled materials like EnduroPlank offers even greater environmental benefits while maintaining safety and functionality. Ultimately, a mixed material approach using traditional materials where essential and sustainable alternatives, wherever feasible, offers the best path forward. This project has deepened our understanding of sustainability in construction and helped us develop critical thinking around material choice. As future professionals in the built environment, we hope to contribute to a construction industry that balances performance with economic, social, and environmental responsibility. Thank you again. Goodbye.